Have you ever wondered why a hot cup of coffee gets cold, or how an engine makes a car move, or even why your own body stays warm? The answer to all these amazing questions and so many more lies in a field of science called thermodynamics. That's a big word, I know. Let's break it down. Thermo means heat. Think of a thermometer. Dynamics means movement or power. Think of dynamite. So thermodynamics is the science of heat and energy on the move. So why should we care about thermodynamics? Well, because it's everywhere. It's the reason we can cook our food. It's the reason our refrigerators keep things cold. It's the reason cars, planes, and trains can take us to amazing places. Without understanding the principles of thermodynamics, we wouldn't have power plants to generate electricity for our homes, schools, and hospitals. Before we dive into the big laws, we need to get friendly with 4 key players in the game of thermodynamics. They are energy, heat, temperature, and work. First up is energy. Energy is the big one. It's the capacity to do something. It's the go power of the universe. It comes in many forms, like the chemical energy in a battery, the electrical energy in a lightning bolt, the light energy from the sun, or the kinetic energy of a moving baseball. Energy can't be created or destroyed, but it can change its costume. Alright, let's get to the laws. The very first law of thermodynamics is a big one. It's also known as the law of conservation of energy. It states that energy cannot be created or destroyed. It can only be changed from one form to another. Think of it like a cosmic accounting rule. The total amount of energy in the universe is constant. Here's a simple example. Imagine you have a flashlight. It runs on batteries, which store chemical energy. When you turn the flashlight on, that chemical energy is converted into electrical energy, which flows through the bulb. The bulb then transforms that electrical energy into 2 new forms: light energy, which helps you see, and heat energy, which is why the bulb gets warm. So, if the first law says you can't win, the second law of thermodynamics says you can't even break even. This law is all about direction. It tells us which way energy prefers to flow. The second law says that heat will always naturally flow from a hotter object to a colder one. It never, ever goes the other way on its own. For example, a hot cup of tea will cool down as heat flows into the cooler air of the room, or a cold drink will warm up as heat from the warmer room flows into it. This law also introduces a very important concept called entropy. Entropy is a big word for a simple idea. It's a measure of disorder or randomness or messiness. The second law states that in any isolated system, the total amount of entropy or messiness will always increase over time. The universe is constantly moving towards a state of greater disorder. Think about your bedroom. It's easy for it to get messy, right? Clothes on the floor, books out of place. It takes effort and energy to clean it up and make it orderly. The universe is just like that. We've covered the first and second laws. Now it's time for the third law of thermodynamics. This one is all about the ultimate cold. It deals with a theoretical temperature called absolute zero. Absolute zero is the coldest possible temperature that can exist. It is 0 on the Kelvin scale, which is equivalent to minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. At this temperature, something very special is supposed to happen. All the jiggling and wiggling of atoms and molecules would completely stop. The third law states that as the temperature of a system approaches absolute zero, its entropy approaches a minimum value. In a perfect crystal at absolute zero, the entropy would be exactly 0. Now here's the really interesting part of the third law. It also implies that it is impossible to actually reach absolute zero through any finite number of steps. We can get incredibly close, but they can never get all the way there. You might be thinking, hey, why are we talking about the zeroth law after the first, second, and third? That's a great question. It's because scientists came up with the first 3 laws first. Later, they realized they needed one more very basic law to make everything logically complete. So they cleverly called the new one the zeroth law. It's so fundamental it comes before number 1. This law is all about thermal equilibrium, which is a fancy way of saying having the same temperature. The zeroth law states this: if object A is in thermal equilibrium with object B, and object B is in thermal equilibrium with object C, then object A must also be in thermal equilibrium with object C. Now that we know the laws, let's put them to work. To do that, scientists talk about a system and its surroundings. Let's head to the kitchen, which is a fantastic thermodynamics laboratory. Consider cooking pasta. Your system is the pot of water on the stove. You turn on the burner, which transfers heat energy from the surroundings, the flame, into your system, the water. The water's temperature rises, its molecules start jiggling faster. How about a refrigerator? Its job is to defy the second law, but it can't do it for free. The second law says heat naturally flows from hot to cold. A refrigerator does the opposite. It moves heat from a cold place, inside the fridge, our system, to a warmer place. Your kitchen, the surroundings. How? It uses work. An electric motor runs a compressor which does work on a special refrigerant gas. This process absorbs heat from inside and dumps it out through the coils on the back of the fridge. This is why the back of your fridge feels warm. So there you have it. We've journeyed from the basics of heat and energy to the 4 fundamental laws that govern them. We've seen how thermodynamics isn't just some dusty old science but a vibrant and essential part of our everyday lives. It explains why we feel cold in the winter and why a campfire feels warm. It dictates how we power our cities, how we travel across the globe, and how our own bodies function. Understanding these principles is more important now than ever before. As we face global challenges like climate change and the need for sustainable energy, thermodynamics is at the very heart of the solutions. How can we build more efficient solar panels? How can we design power plants that produce less waste heat and pollution? How can we create better batteries to store energy for when the sun isn't shining or the wind isn't blowing? The answers to these critical questions lie in applying the laws of thermodynamics in smarter and more innovative ways. It is the science of efficiency and sustainability. So, the next time you sip a hot drink, start a car, or just feel the warmth of the sun on your face, take a moment. Think about the incredible journey of energy that made that moment possible. You are witnessing thermodynamics in action. It's not just a topic in a science class, it's the very script of the universe, written in the language of energy. And the more we learn to read that script, the better we can understand our world and our place within it. Science is for everyone, and thermodynamics is a beautiful place to start. Consider it. Have you ever wondered why a hot cup of coffee gets cold, or how an engine makes a car move, or even why your own body stays warm? The answer to Have you ever wondered why a hot cup of coffee